So once I solve for A, once I solve for the measure of arc XZ, I can go ahead then and find its length. Its length is going to be equal to however many degrees I have over 360 times that total distance around. So my circumference is going to be twice times pi times my radius. If I wanted to find the area of that sector, if I want to say, okay, let's look at what this area of this sector is, it is the same exact conversation where I can have this same part of the conversation, but the only thing that's different now is instead of writing 2 times pi times 5, I'm writing pi r squared. When I'm talking about my area, it's a piece of that area. If I'm talking about my length of my sector, then that's not. What's the matter?
It is area of sector YZW. So
Darn it. YZW is my other one. So what's going to change in
It's
this?
going to be 52.
Then this is going to be 52 degrees out of that 360. You need to know how to do that calculator work. If you don't, you need to raise your hand and ask. Minor arcs, major arcs, semicircles, length and area of my arcs and my sectors. You feeling okay with that? All right. The last class we threw a lot at you with tangents and chords. And so we want to make sure that we review and put all these big ideas on one paper. If a radius is drawn to a tangent, then the radius and the tangent are going to be perpendicular. Any radius drawn to a tangent is going to be perpendicular. If I have 2 segments coming from the same external point, 2 segments coming from the same external point, then, and touching my circle at one point of tangency, then that means the segments are congruent. So those are our 2 tangent conversations. We had converses involved in that too. So if a radius and a segment are perpendicular and it touches at one point, it's tangent. And we went ahead and proved this using CPCTC and congruent triangles. Next, we started talking about chords of our triangles. Circles. And our chords are congruent. Our chords are congruent if the arcs are congruent. And the arcs are congruent if they have the same central angle. So we want to make sure that we understand the relationship between the chords are congruent if, and we call it the related arcs are congruent. And then we also talk about the central angles are congruent. There's one more conversation here, and that's going to be for this picture here, and that involves these segments. What is that rule? The chords are congruent if, yeah, if they're the same distance from the center. I liked Kenley's word, equidistant from the center. So picture pushing those two diameters out. And I like this conversation here. If I think about this diameter here, and I'll go ahead and make it so it's an exact diameter. When I go to push this diameter out from the center, whatever distance I push that diameter out, if I were to push this diameter out, get my two segments set up. If I were to push this diameter out too, that those distances that they are hanging out outside the circle are going to be the same, because they started off the greatest width of the circle and were pushed out. Whatever distance they were pushed out, we have the same amount of hangover outside the circle. So those chords are going to be the same. We started to talk about this, but we never finished it last class when we talk about having two of the three features. And we said, if you have a diameter, and that is going to be a special kind of chord that goes through the center of a circle. If that diameter is perpendicular to a chord, then it's going to bisect that chord. And we talked about any two of those three are going to give you that third. So if you have a chord that's bisected and perpendicular to another chord, that chord's going to be the diameter. If you have a diameter that bisects a chord, it's going to do it at a perpendicular relationship. So anytime you have two out of the three, anytime you have two out of three, whether it's these two or the top and bottom two, you automatically have the third. We want to revisit our warm-up, the back of it. And this is a real-life application. If you have a rescue beacon, you're a backcountry skier. In fact, now it's not even just backcountry skiers. In the new ski camps that I bought, there is a tag that sends out a signal with were I to be buried in an avalanche, don't you fret, they will find me using this geometry. Are you ready? So the way this works is like this. I am somewhere in the center of this circle, buried under an avalanche of snow. The signal that's in my ski pants sends out a signal, and that signal is communicated in this circular path. Are you with me on that conversation? So if a member of ski patrol is walking along, can he hear the signal here? Can he hear the signal here? Yes. Here? Here? Here. Here. So that signal sends out a circular path. So when that ski patroller walks up and hears the signal, he has no idea where he has hit this circle. He has no idea if he's come across the very top of the circle, the side of the circle, the bottom of the circle, or the middle of the circle. So what he's going to do is, as he's walking along, he's going to draw or mark the spot where he first heard the signal. Does that make sense to you? All right, so this is where he first hits the signal. Then he's going to walk until he doesn't hear it anymore. And he doesn't know what direction to walk in. He doesn't know if he should walk this way. He doesn't know if he should walk this way. He doesn't know if he should walk this way. And he doesn't know if he should walk this way. Does it matter which way he walks? Because he's going to hit the outside of the circle no matter where he goes, right? Are you okay with that? So let's say he walks straight across this way. Is he hearing the signal now? How about now? No. So he's going to keep walking until he doesn't hear the signal anymore. And then when that happens, he's going to mark that spot. Got it? So then what he's going to do is he's going to look back at this spot and this spot, and he's going to find a measurement. What measurement do you think he wants to find between these two spots? What is he looking for? Let's think about it. We have 3 considerations. We can have, is it a diameter? Is it perpendicular? Or is it a bisector? What do you think he's going to look for with that distance between those 2 spots where he heard the signal? What's he looking for? The bisector. He's looking for the exact middle. So he's going to measure this distance and he's going to bisect it. Once he bisects it, he cuts that distance exactly in half. You okay with that measurement? So here's my ski patrol guy. Keep in mind, he was walking along. Oh, I think I hear a signal. Walk. Oh, I don't hear it anymore. Now he's going to measure this distance and come back to exactly 1/2. You with that? What's he going to do next? What do you think? He's going to find the perpendicular. So he's going to go ahead and start walking again, but when he walks again, he's going to do it at a perpendicular relationship. Now, does it matter if he goes left or right, up or down? So we know that's a longer walk up. He doesn't, because he doesn't know at what point in the circle he has found me. Think about this. This chord, he might be at the top of the circle, right? He doesn't know where he is. So he's going to go ahead and walk up. Can you hear the signal? 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 Once he gets up to here, what happens? He can't hear the signal anymore. So what he's going to do is mark where that happens. And then he's going to make sure that this is a perpendicular line. So here he is at the top, at the top of the circle. He can't hear the signal anymore. What's he going to do now? Come all the way back. So he's going to walk. How far is he going to walk? All the way till he can't hear the signal anymore. And he's going to mark that with this. So now he knows that this is a what? So where am I? Where am I? I'm at the center, which is the halfway point. So when he wants to find me, he needs to measure this whole distance across the circle and find what? The exact middle place, because this is where I am. And he's going to dig me out. There's Mrs. Leisure, saved. These steps are described to you at the top, but what you think about is he has a bisected chord, he has a perpendicular relationship, and then a diameter that goes through the center of the circle. So if you have a bisected chord and a perpendicular relationship, what you end up is the diameter, and the diameter is a special kind of chord that goes through the center of the circle. What I want you to do now is turn to your partner and tell the story of how to rescue somebody that's buried in an avalanche. Turn to your partner, go. All right. So last class we went through, and again, think about that curve of forgetting. You want to make sure that you remember. Now, let's go ahead and make sure that your warm-up, let's make sure that your warm-up has the right things marked. It says, walk until a signal is detected and mark that spot A. That is what we did first. A. Continue walking a straight line until the signal disappears. Mark this spot B. That's what we did there. Turn around and pace the distance between the point and come back to the halfway point. Mark that point C. We'll call this my halfway point. Walk away from the line at a 90-degree angle until the signal disappears. Mark this point D. That's what we did here when we walked away. Turn around and pace the distance in a straight line until the signal disappears again. Mark that E. That's going to be this point here. Pace back to the halfway point, and that halfway point is F for you found me, because that is where I am buried under the snow, and hopefully you have saved my life. Real life application of diameters, chords, perpendicular bisectors, right there for you. All right, last time we talked about these properties of tangents and chords. So I want you to scan your eyes over and think about what kind of problems we end up with. Anytime we have a relationship that's perpendicular, get yourself ready for some right triangles and Pythagoras. And then we went ahead and talked about the properties of the chords and arcs. That relationship between the central angles, the chords, the arcs, when it comes to their measures. In the same circle or in congruent circles, two minor arcs are congruent, their corresponding chords are congruent. Got it. Our next conversation we had was these chords that are equidistant, and I always think about somebody pushing those chords away from the center of the circle. If they're the same distance, then they're going to be congruent. And then here's our buy two, get one free conversation. You have the third. Now, I asked you to finish this page for homework, and this was our practice for this section. So we can quickly talk about this, find the measure of each arc. So if I want to know the measure of arc D to G, that's going to be 150 degrees. From D to G to H, that's going to be, let me do some math here. So it's 270. Do you get T is 90 degrees? Did you get that? So that means that from D to G to H is 270 degrees. And D to H, 90 degrees. Thumbs up if you agree with me. Okay. In circle X, AC is a diameter, and segment ED is congruent to EB. So let's go ahead and draw them. Segment E to B is congruent to E to D. What can you conclude about arcs DC? Here's arc DC and arc CB. Try and talk to your group mates about what you were able to conclude. And Marcus said go. So there's a bunch of different conversations you can get from this. Give me one. Talk to me about DC and CB. What do we know about them? Yeah, they are to be congruent. Do we know why? What does that one say?
If the arcs are congruent, the arcs are congruent, and the chords are congruent.
If the arcs are congruent, then the chords are congruent. But we need to be careful here because those segments, ED and EB, are not radii. and they're not chords because they don't have endpoints on the circle. So this is a conversation about bisecting. This is an interesting one because I have AC as a diameter and it's bisecting this chord here, dB. So these arcs here are going to be congruent. That's an interesting thing, that we don't have diameter or that we don't have radii. So if chords are congruent, then their arcs are congruent, but those arcs don't come from those chords. So the best thing that we can say is that this segment is bisected, but then we're doing some assuming of, I don't know, we're given this. I'm gonna come back and look at this in a minute. I don't like that picture. We'll come back. This one I know for sure. Diameter perpendicular, therefore it's bisected. If I want to find the measure of arc KM, I know that this is a diameter. I know that this is perpendicular, so therefore I know that these are bisected. So then I know that this arc here is also bisected. So 7x minus 16 is going to be equal to 5x. So 2x is equal to 16, x is equal to 8. If I want to find the measure of k to m, then the measure of arc km is going to be equal to 5 times that value of x, which is going to be 40 degrees. Are we good with that? Yeah, that one we like. Find the value of x to the nearest 10. All right, so this can be a piece of a diameter and it's perpendicular, so that means that this is 7 and this is 7 because this is a diameter, this is 9 and this is 9. So the Pythagorean theorem tells us that 7 squared plus x squared is going to be equal to 9 squared. So x squared is equal to, we have 81 minus 49, which is 32. So then x is going to be equal to 4 roots of 2, to the nearest 10. So second radical 32, 5.7 units. Does that look good to you? Okay. So we have a radius of 15, a piece of the diameter that's 8. So we're going to go ahead and solve for this value here. I'm going to call it A so you're not confused. But 15 squared is equal to 8 squared plus A squared. So 15 squared is 225. Is equal to 64 plus A squared. So when we do 225 minus 64, and then take the square root because they want us to round. Nope, that's not what I want to do. Second radical, second answer. 12.7. That's going to be A. So then x is going to have a value that's double that, right? So times 2. 25.4. Go by that. X 25.4. Are you okay with that? Alright, let's see what we can do here. Here we have what looks like a piece of the diameter. It's perpendicular. So this 10 is going to be 5 and 5. And they tried to mess you up by asking for the radius, but you're allowed to draw a radius wherever you want. So 5 squared plus 4.2 squared is going to be equal to x squared. So 25 plus 4.2 squared plus 25 is equal to that second radical, second ants, 6.5. So that means that x is sort of equal to 6.5. How are we doing on that? All right. When you have your next work time, your next two pages where instead of the Delta Math, we had this practice. We didn't like much of what the Delta Math had to offer. So instead we wanted to give you this. This key is posted on Schoology. So if you go to our Schoology page and our folder on circles, this practice key is here. And you're welcome to check your answers and let me know how you did. In 9.4, we introduced the idea of an inscribed angle, an intercepted arc, an inscribed polygon, and a circumscribed circle. So all of those are words you've already had before. But before we go much further, I want to have a conversation about which is the best seat. So here's a picture of a movie theater, and I want you to picture that movie screen is your diameter. What you have drawn over and over again, and I'm sorry if your copies are dark, what you have drawn over and over again is what we call an inscribed angle. An inscribed angle is an angle that's inside of the circle where the vertex is on the circle. So if you look here, I have this inscribed angle here. If you look here, I have this inscribed angle here. I have this inscribed angle here. This inscribed angle here. This inscribed angle here. So let's go ahead and number these. We have point 1, we have point 2, we have point 3, we have point 4, and point 5. What I'd like you and your group to quickly decide is if you're walking into the movie theater, which is the best seat? Turn and talk about it. Go.
3.3.
I heard lots of 3s. Anybody say 1? Anybody say 2? Anybody say 4? Anybody say 5? Here's the good news. There is no best seat. Because every single one of these angles compared to the movie theater is the same. Every single one of these angles is the same because they are all inscribed angles from the same intercepted arc. And that intercepted arc that they have is going to be this whole conversation around one face and then the other half of that circle around the other. If I have an inscribed angle in a circle, its measure is half of the arc. So when we talk about the measure of angles, we're used to having this central angle that has this measure of x degrees, and we're used to having this arc with the same measure. Today we're talking about this measure of the arc in here, which is going to be 1/2 of what x was. So I want you to think of like a slingshot or a bow and arrow. Think about when you pull something back, that slingshot gets, that angle gets skinnier and skinnier and skinnier. So when I have this angle with its vertex on the center of the circle, and then I take it and I pull it back, and set its vertex on the circle, that angle measure is going to be 1/2. So the intercepted arc is arc AB in this story. So the intercepted arc here is arc AB. The angle that's inscribed is angle ADB, and that measure of that central angle, ACB, is the same as the arc. So given this one theorem, we end up with 3 different corollaries. And remember, corollaries are, oh yeah, while we're here, let's talk about this. And again, if you want some colored pencils, I have them on the round table, but I want you to see something, and this is crazy. Do you see arc AB? Do you see inscribed angle? Oops, that's not what I want. Stop. Stop. Inscribed angle ACB? Do you see inscribed angle ADB? Do you see how C and B both have vertices that sit on the circle? If AB has a measure of x degrees, both of these arcs come from the same endpoints on the circle. Do you see how they both start and end at A and B? And it doesn't matter where that vertex is on the circle, they're both going to have the same measure. So the measure of C is 1/2 of the arc. The measure of angle D is 1/2 of the arc. Therefore, 2 inscribed angles that intercept the same arc are going to be congruent. So those 2 inscribed angles are going to have the same measure. All right, here's another, oh yeah, corollary. If I have a semicircle, what is the measure of this arc? If I have a semicircle, the measure of my central angle is 180 degrees because it's a straight angle. And the measure of my arc is 180 degrees. So what do you think the measure of my inscribed angle is going to be? 1/2 of that. So if an angle is inscribed in a semicircle, it is a right angle. All of those angles in the movie theater were inscribed in a semicircle. They were all 90 degrees. Now this one I find so very cool. The opposite angles of a quadrilateral inscribed in a circle are supplementary. So watch first and then do. So put your pencils down and just watch me do this because it'll make sense to you after you see me do it. So let's talk about this. We have a quadrilateral that's inscribed in a circle. The word inscribed means that each of its vertices is sitting on the circle. I wish I knew why my board did this. It drives me nuts. So each of those vertices sits on the circle. You okay with that? So this green arc, this green central angle comes from this intercepted arc. Are you okay with that? So this angle E is created from this arc. Do you see that? Now I'm going to do something else. Are you ready? Do you see point G? Do you agree that G comes from this arc? Yes? So do you agree that those two arcs make up the whole circle? So when we talk about this, that means that the measure of arc DEF plus the measure of arc DGF make up the whole circle, right? Aren't the angles half of the measures of the arcs? So what would the sum of the angles be? What's half of 360? 180. So the opposite angles of a quadrilateral are supplementary. All right, pick up your pencils and let's do it together again, but let's use the other vertices. Are you ready? Do you see angle D? Mark angle D. And with some color, go ahead and mark the intercepted arc that forms angle D. There's angle D. It's an inscribed angle from that arc EFG. Yeah? You good? In another color, I'm going to then talk about F. So here's angle F that is inscribed from this intercepted arc. Because I know that arcs red plus arc blue is 360, that means that angle red plus angle blue equals 180. Opposite angles of a quadrilateral that's inscribed in a circle are going to be supplementary. They're going to have the measure equal to 180 degrees. Next one. If a tangent and a chord intersect in a point on the circle, then the measure of each angle formed is 1/2 the measure of the central arc. So here's our tangent line, A. And here's its point of tangency, where it touches the circle exactly once. It's telling you that this angle here, the measure of the angle formed by the tangent and the chord, is 1/2 of this arc. So if this is x, this is 1/2 of x degrees. And to me that makes sense, because if I picture a tangent, or if I picture that intercepted arc becoming wider and wider and wider and wider and wider and wider, point to the point of where it's tangent, my inscribed angle becomes wider, 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 wider. And again, we can talk about the relationship between supplements, because if this arc measure, we'll go ahead and call it y degrees, this angle is going to be 1/2 of y. I know that x plus y is equal to 360, so 1/2 plus 1/2 x plus 1/2 y would be equal to 180. Lots of circle fun facts, and if you take them bit by bit, they can make sense. So here's what I want. Here's some practice for you. With your group mates, go ahead, find the measure of each arc, work your way through 1 and 2, see how far down you get, and we'll check in a minute. Off you go. Get busy. Work. All right, let's come back. Lots of good conversations out there I'm eavesdropping and listening to. Lots of people sitting there doodling on their papers, not doing any math. And they're going to go ahead and copy down my answers. How much do we learn from copying? So while you're here, you need to make the most of your 90 minutes. If your group isn't talking, sharing, collaborating, or working together, what an amazing leadership opportunity for you. If you say in your group, come on, let's go, I want to figure this out. All you gotta do is ask one person, what did you get from this answer? Or how did you do this? Because then that lets you keep going. If you're working ahead onto next pages, I'm gonna ask you to come back because I want everybody on the same page as me. So finish your thought and come back so we are all looking at the same page. Check in with your group and tell them all, dude, go back to where she's working. Number 1, find the measure of the arc or angle. Are we all there? Find the measure of the arc or angle. Because I know that this arc from X to Z is 140 degrees, so is the central angle. So the central angle and the intercepted arc, same angle. This one, picture that pulling back, 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 back. What is the relationship? It's going to be half. So 1/2 of this X value is going to be this. So we have a arc measure, an intercepted arc, an inscribed arc measure, angle measure of 70 degrees. Are we okay with that? Here we have our inscribed angle that has a measure of 80 degrees. So this arc that created it with endpoints P and R is going to be double it. You okay with that? So the big conversation for this is going to be, am I halving or doubling? Am I halving or doubling? And we want to think about what's going to make them equal. If you multiply this by 2, they're equal. If you cut this in half, then they're equal. So think about that relationship, which is bigger, the distance around a circle, and make sure that you keep this in your head. The distance around a circle is always going to be 360 degrees. The distance across a line is always going to be 180 degrees. So when you think about where's that 2-to-1 story, keep in mind, am I talking about my trip around the circle or my trip through it? In number 2, my measure of angle Y is 62 degrees. So here's my inscribed arc with its endpoint on the circle. Therefore, any other angle that is also sitting on the circle with the same exact endpoints, W and X. Think about it. Are you with me? Every single seat in that movie theater has the same angle. So that measure of angle Z is 62 degrees because they both have the same intercepted arc. Do you see this? W and X, W and X, W and X. Are we good? Next up, where am I? There we go. Find the value of X. Because I know that this is a chord that goes through the center of the circle, I know it's a diameter. So that means that this arc, 180 degrees, and this straight line have the same measure of 180 degrees. That tells me then that this inscribed angle must be a right angle, so I can use that knowledge to solve for X. You are in one of 2 camps here. You're either blue or green. You only need to use one of these stories, but either you're going to double your angle to equal your arc, or you're going to half your arc to equal your angle. Now, if these are friendly numbers, there's nothing wrong with going along this route of 4x is equal to 6x minus 50, and having 50 equal to x, and therefore x is equal to 25. Not a problem here. Typically, kids like to double this because if these numbers are odd, they're dealing with fractions. Not in this case, though. if you solved 8x is equal to 12x minus 100, you would get the same, x is equal to 25. The biggest mistake here is that you double or half the wrong value. So keep in mind, your angle is coming from your straight line, and that is going to be half of that distance around the arc that's created. Everybody okay with that? All right, when I look at 5 and 6, I've got the same story. I doubled my angle to equal my arc. I could have halved my arc because those are both even numbers and friendly, but instead I did 10x minus 20 is equal to 8x plus 32. Not a problem to then solve for x. Here when I have a quadrilateral that is inscribed inside of a circle, I know that my opposite angles are going to be supplementary. So 18y plus 126 is equal to 180, and 72 plus 18x is going to equal 180. That is because when you look at these endpoints, they take up the whole circle together. Let me fix that. Here's this endpoint here. And this guy's endpoint is there. They take up that whole circle, so that's why 18x plus 72 is going to be 180. All right, we have one proof in this section. Given circle O, write a paragraph proof that's proving that triangle MEI, here's triangle M to E to I, is, what's this mean? That it's similar to triangle GED. So if you didn't get this far with your group, I would like you to turn to each other and just tell me some ideas that you have on what you need to prove similarity and how you might do it on your market set talk.
Vertically, the most similarity is like
Alright, so we can and then we can do vertical angles because the corollary is one. It's angle similarity.
Yeah.
Because this corollary of which is two inscribed angles that intersect the same arc are equal. And I and D, and the lines that go up,
so that
they
means
both
our
go
measures are
to
the
M
same.
and G. So that means that vertical angles,
There's like something.
and then you got angle similarity.
I feel like that's enough of
This like corollary.
What does it say?
It doesn't have like a name, but this is it. Because like, or I know it's not, but like yeah, it makes. The other one is just not English. And how they test, and then the essay. The test, the essay is all doing like yeah, like this week. That's 3 like actual assessed things in like 2 weeks with SLS and like finals coming. Is it really useful? She's good. I don't know. Like, and it's just like
All right, what do you tell me that you see that you know? Given circle O, write a paragraph proof. So we'll go ahead and start our paragraph proof. Given circle O, what do you know? Name something that you know. I what?
Angle I and D.
So angle I and D are congruent. So I know that angle, let's call them by their full name. IEG is going to be congruent to angle MDG. So just so we got some perspective, he's talking about this angle is congruent to this angle. How come?
Isn't it both like in the same arc? Inscribed arc?
Are because they are inscribed angles from the same intercepted arc. So do you see this arc GM? And you can go ahead and say the same intercepted arc MG or GM, it doesn't matter. So because I have those same inscribed angles that are created from the same intercepted arc, I know that they are congruent. What else do I know? Lots of choices here. What else do you know, David? Why? So you have a couple choices here. David chose to do vertical angles. So he says that angles MEI, angle MEI is going to be congruent to angle, here's MEI to GED, because they are vertical angles. Could I have talked about angles M and G? Could I have used inscribed angles for from arc ID? Do I need to still do that? I can prove those angles congruent by either my third angle theorem or by intercepted arcs, but we all agree we don't need them. How come? Therefore, by angle similarity, triangle MEI is similar to triangle GED because they have two congruent angles. Pretty cool. Alright, here's what your homework is that I want you to take a look at. We gave you a delta math for 9-4 for you to do, and one more page of inscribed angles. So this page for homework, but I also want you to take the time to check your answers from last class's homework. So this homework on tangents and chords, I want you to take a look at. So you've got a delta math, and then you've got to go to Schoology to check your work, and then you have this page in the packet. I can't say it enough times. If we learn 3 or 4 new relationships between circles every day, in 1 week's time, you have like in excess of 10 things to remember. And I was hearing one student say, and I've got this in that class, and this in that class, and this in that class, and SOLs, and I've got practice, and I've got sports, and I've got, there's a lot going on. Welcome to spring. That's what spring is. So you have to walk into this room and make a commitment to make the most of your 90 minutes. When you walk in the room, you are a geometry student with laser focus and hyperattention. Make sense? All right, you've got a couple minutes now. Go ahead, don't pack up early, but you've got a couple minutes Can you knock out a couple questions? Either finishing up the ones that we scooted through too quickly for you, or scooting on and starting to look at these. I bet you could finish these first three before the bell rings on your market set go.
Maybe you get 6.